Hi, this is Dan Bullard, retired electronics engineer sitting on the front deck of my houseboat. It's the 23rd of July. My birthday's only like 6 days away, so yay, I'll be 69. Okay, I've talked about this in another video, but it's like a 45-minute long video, and I don't think you've got 45 minutes, so let's make it quick. Years ago, I was sitting in class at Northern Telecom down in Rancho Bernardo, California, and we had a contractor who was a former employee of LTX teaching a class on codecs, telephone codecs, to the Northern Telecom people, and my boss arranged that, and I got to be a student in that class. And during that class, he was talking about aliasing, and I had never heard anybody explain aliasing before. So I listened very intently, and he came up with something like this. Crazy. Now this is what Google Gemini says you should do with aliasing to calculate where an alias will go. So if you're sampling a waveform, and if say you're sampling a waveform at like 30 kilohertz, and the alias, the signal you're going for, is like 50 kilohertz or 70 kilohertz or 80 kilohertz, where does it go? Because it will alias back unless you use an anti-aliasing filter. It will alias back into the Nyquist band, and you need to know where it went. Now, everybody thinks about it this way, the way that Google Gemini does. And this instructor who worked for LTX did it the same way. And I followed along, and I didn't like it. And this is why I didn't like it. So here it is. I said I have a spectrum showing a sine wave aliasing from a higher frequency. How do I calculate what frequency it is? Calculating the original frequency of an alias sine wave in a spectrum requires knowing the sampling frequency, f sub s, of the system that generated the spectrum. Here's how you can do it. Identify the aliasing frequency. Look at your spectrum and find the apparent frequency, f alias, of the sine wave that you suspect is aliased. This is the frequency shown on the x-axis of your FFT plot. Understand the Nyquist frequency. The Nyquist frequency, f Nyquist, is half the sampling frequency. F Nyquist equals f sub s over 2. That's true. This is the maximum frequency that can be uniquely represented by the sampling rate. Frequencies above f Nyquist will fold back into the spectrum below f Nyquist. Apply the aliasing formula. The general formula for aliasing is based on the idea that frequencies folding around the Nyquist frequency. If your alias frequency, f alias, is observed in the spectrum, the true frequency, f true, could be one of several possibilities. One of several possibilities. Give me a break. Okay? In testing, you do not have that option. You're not going to guess what it is. You don't have several possibilities. So case 1, f true equals k, f s plus minus f alias, where k is an integer, blah, blah, blah. So it goes into a whole big thing, and you can look it up on Gemini. And I hate it. I really hate it. This is the thing that drove me crazy. The instructor, he was a nice guy, Greg Willis, I think it was. He was giving the class, and I listened to it, and I didn't like it. I didn't like it. And that's the same thing that Google Gemini says. By the way, every other AI responds the same way. They all have been trained the same way. Now, in the end, it wraps it up. Without additional information, you can only provide a list of possible true frequencies, as the alias phenomenon introduces an ambiguity. No, it doesn't. Not at all. Now, I was sitting in this classroom learning about codecs, and, I should have known this stuff, but I didn't. But they were good enough to teach me. So I looked into it, and I realized okay, this is a problem. And then I thought about it. Well, my brain twisted on it, and I finally got it. So I explained to Google Gemini that I developed a simple pair of instructions that can be implemented in C, Pascal, or any language to solve this. It's known as Dan's rules. There are 2 rules. Rule 1, if bin is greater than n, bin equals bin modulo n. And if bin is greater than n over 2, bin equals n minus bin. That's it. 2 rules. 2 rules. What did Google Gemini say? That's a clever and concise way to describe the common method of handling aliasing spectrum, specifically for mapping all alias frequencies back into the Nyquist zone. Your Dan's rules effectively encapsulate the following behavior, and it goes on to explain what it is. If you're sampling at, say, 30 kilohertz, then everything up to 30 kilohertz could or could not be aliasing, but if you go beyond that, it definitely is aliasing. So if I use my rule 1, I move everything all the way back to the first band, from DC to F sub S. So that's the meaning of rule 1. If bin is greater than n, bin equals bin modulo n. Modulo is the remainder operator, so it just takes care of it. Now, they do it in a similar way, but they do it wrong. I don't like the way they do it. Now, once you get it into that band from DC to F sub S, you got to figure out if it's reversed, if it's flipped, aliased backwards, or is it regular forward? And so then you use rule 2. So you have to use rule 1 first, then you use rule 2. Now realize you don't really have to say if, because if bin is greater than n, just do it. Modulo doesn't hurt anything if it's not greater than n. So just say bin equals bin modulo n, boom, you're done. You don't have to say if. So you can save a tiny bit of time. Rule 2, however, you do have to do the if. If bin is greater than n over 2, bin equals n minus bin. That's all there is. So if it's aliased from F sub S over 2 up to F sub S, then it's reversed. You've got to flip it. And that's what n minus bin is. Now, it works like a champ. It works so good. And it was really cool because back when I was doing this, I figured this out, and then I started teaching it in all my classes. So one time I was teaching a class to a bunch of students, and I didn't realize who they were. Just, 2 weeks you get a class, you teach them, and they go away. But 2 of the students were going to be engineers for Credence. So teaching this class, the 2 engineers were getting schooled on the machine so that they could go off and write code for the machine. That was Vista, Credence Vista. And so I was explaining Dan's rules, and I told them, now here's the thing, and I explained how it all works, and I explained how Dan's rules work, and I explained that the software in the tester does not accommodate that. So none of the routines that look at THD or signal noise or any of that stuff deal with aliasing, and so just get used to it. Now these 2 software guys were pretty smart. They came up to me on the next break and they said, just to let you know, we're joining the software engineering department, so we're going to get to write software for this machine. Would you like to have your rules incorporated into the software? We can do that if you don't mind. I mean, do you copyright or anything, or is it something we can use? I said, hey, more power to you. If you can do that, that would be wonderful. So they went in as software engineers now. They finished the class, they went in and they did this. They wrote the code and they put it in the machine, and boom. Suddenly the Credence Vista had the ability to do THD and signal noise ratio and various other things by looking at aliases. So if a harmonic alias, you say the 8th harmonic alias, and you're looking for THD, it could figure out where the 8th harmonic was, and it could calculate when it aliased. So it's pretty cool. Now another really cool thing about this is, notice that it uses bins. The Google Gemini method uses frequencies. So you calculate frequencies. Frequencies are floating point numbers. So what that means is you're doing floating point math. Now, we talked about this before. Floating point math versus integer math. With floating point math, there's some ambiguity because you get rounding, and you don't really want to do that. With integer math, there's no rounding. Everything's an integer. So if you stay with bins, Dan's rule, it's all integers, you're never going to have any rounding. That's a big thing. That's a really big thing. So remember Spice, they used 32-bit floating point numbers. They were subject to rounding, but even with Excel, you had 64-bit math. There wasn't much rounding, but I wouldn't trust it. I don't trust floating point numbers very much. So stay with integers if you can. So that's the great thing about Dan's rules, is that it uses integers, not floating point numbers. So it's pretty cool. I tried this out on Gemini, I tried it out on Grok, I tried it out on ChatGPT, and I tried it on Leo, and they all agreed this is the right way to go. Now, of course, will they remember it? No, because that's considered, confidential between the user and the tool, and they don't remember things. It can't go in the forward in the future, but you can carry it forward. Dan's rules. Look it up. It's on this page on my webpage. Dan's rules. A big deal. I figured it out myself. It's my invention, so it's pretty cool. It's Wednesday. You'd think everybody would be home or wherever they want to go, but it's going to be a nice day, so people are taking the day off cruising the river. So once again from the river, this is Dan Bullard. See you.